Hello and welcome back to Patch Math, where today we are going to continue your patching your math knowledge on graphing trig functions using the unit circle. The number one thing students will get wrong here is they will mix up their variables because the x and y values that are on your unit circle are not the same as the x and y values that are going to be on your graph. And I, as a student, took a very long time to figure that out. But once I figured it out, this became my favorite method because I no longer had to memorize a bunch of facts about transitions, translations, dilations, whatever you want to call them, of parent functions of trig, uh, or parent functions and of trig functions. Yeah, parent functions of trig functions. I could just use a little bit of information about their characteristics instead to choose my x's wisely, take those wisely chosen x's, and then follow the series of steps. I went ahead and in the last video named the x value and the y value on our unit circle x sub u and then a y sub u for the x and y on the unit circle. Subscripts are commonly used to differentiate repeating x and y values like that. If you leave the x's as the exact same thing, you are technically wrong because you'll be saying two different things are the same x. I don't like the fact that the y's repeat. I actually prefer to use what f of x here. And the reasoning behind that is because it tells me which variable goes with my output. It's x. So I don't have to worry about subscripts at all there. And you'll go ahead and notice that I have written it out like that there. Now, how do we wisely choose our x so that the rest of the steps flow? Well, if you go ahead and look here, you'll see that our x is in the numerator of a fraction. If we're going to write that out a little more plainly, we could also see that fraction as tangent of this. We can pull that 1/4 out front. That's 1/4 times x. If we were to combine it back together, x would just go in the numerator with that 1, and there we are. So why does this matter? Well, that 1/4 is what we call b. All right. And that's one of those things that you're taught whenever you are memorizing your parent functions of your trig functions and their translations and shifts and the A, B, and C and how they interact on them. And that's a mouthful. And I'm not even said all the stuff that you have to memorize in addition to that. Instead, we can just find how this changes our period. Now, a traditional period for a tangent function is just usually pi. So watch what happens to the period here. We take a usually pi period and we take pi. We stick that pi over 1/4, and we have a particular type of fraction that students do not like. Please don't fret. We can keep the numerator. We can apply what's called keep, change, flip. Keep the numerator. All right, keep the numerator. Flip. And actually, let me put a note on that. There we go. So we can choose to keep the numerator, and we can choose to change the division to multiplication, and we can choose to flip the denominator, and the denominator is 4. And I'm using parentheses to represent multiplication there. And so now our new period is 4 pi. Well, normally a tangent, and let me go ahead and just bring up the parent function just a minute. There we go. Tangent normally has a period of pi, and we usually look about between the vertical asymptotes about the origin. So we have a vertical asymptote negative pi over 2 on our parent function and pi over 2 on our parent function, and the distance between negative pi over 2 and pi over 2 on our parent function is pi. Well, what we just discovered is that is no longer pi. This is now 4 pi. How does it change things? Well, it takes everything and expands it outwards by a factor of 4. So now we no longer have pi over 2. That's 4 pi over 2, which is 2 pi, right? I'm going to cancel all the rest of stuff. Don't worry about this. Just showing you how you would do it in your memorizing way. This would be negative 4 pi over 2, which is negative 2 pi, and both of these things have a span of 4. All right, so I said that wrong. Have a span of 4 pi, not 4. Have a span of 4 pi there because the distance between negative 2 pi and 2 pi is 4 pi. All right, now that we've got that visualized, the only reason I want to go those tiny little pieces of information for that horizontal stretch is because we are going to wisely choose our x's from here, and you do need to know your period and a little bit about the basic outline of a trig function in order to choose these. Now we notice that parent functions for tangent are situated about the origin. I'm going to go ahead and start with a 0. Then I know, well, if I need to span negative 2 pi, 2 pi, what falls halfway between negative 2 pi and 0? Well, that is pi, negative pi, pardon me, and halfway between 0 and 2 pi, that's pi. So step 1, we wisely chose our x based on the period. Then we're going to take that x, and it is going to get put in here. So this x value goes right here. The last video, our x and theta happened to be equal. In this video, they are not. You'll see that our x happens to be 2 pi. We will put that over 4. And we'll find that theta equals pi, negative pi, over 2. That makes sense, because what we saw when we were taking on that parent function and bringing it out, we took what was originally a vertical asymptote, negative pi over 2, on our parent function tangent, and we dilated that, expanded it by a factor of 4. Well, we look there, that is negative 2 over pi. So that's what you're doing when you're doing those shifts by the memorizing. This is the mathematics that goes behind it. We're just going to repeat that pattern over and over and over again. This negative pi goes in there for x. This is negative pi over 4. There's no simplifying that needs to be done there. Then we're going to take that 0 and we're going to put it in for your x. This is 0 over 4. And that is 0, which makes sense. If you multiply 0 by anything, you get 0 back out other than something undefined. That is important. So pi goes in the numerator again. This is pi over 4. And 2 pi goes in the numerator again. And this is 2 pi over 4, or pi over 2. What you're going to see, this is the points, the thetas that you get are generally those points they ask you to memorize on the parent function. This is just how you can get them right back out if you wisely choose your x's. So this is pi over 2. I can't talk and write at the same time. I don't know why I keep trying, but I do. Now that we have those, it is important to note that these thetas then, all right, so we did step 1, step 2, and then we're going to take these thetas and plug them in here to find tangent of theta. It's super important. Now, we have an extra amount that we will need to put in here. When I say an extra amount, we will need to put in here. What we are finding when we are finding tangent of theta is just this. This is tangent of theta, because theta is x over 4. Those are the same thing. We will have to take whatever we find here and multiply it by negative 2, because tangent of theta and fx are not the same thing. There is that negative 2 out front. That being said, I'm going to go ahead. This is f of negative 2 pi. But you'll see that they're related just by putting them there in the graph. So we're going to have that negative 2 on the outside, and then on the inside, it's whatever our tangent of theta is. Negative 2 on the inside, whatever our tangent of theta is. And that pattern is going to continue. You'll probably have to simplify. I'm just writing out like a skeleton here, so that way I'll have it to refer back to. Now, tangent of theta, well, we take tangent of negative pi over 2. What is negative on a graph? That's super important. So when we are traveling on the unit circle, we generally start here and we go counterclockwise. However, those are our positive angles. However, if you have a negative angle, it means that your angle opened in the opposite direction. We generally find what's called a coterminal angle in order to be able to graph this. We can also look at it as we went backwards by pi over 2. And that's generally how I prefer to look at it. With that being said, we plug in that and we get, if we plug in negative pi over 2 for theta, we end up at 3 pi over 2. Then we will find that tangent of that. Well, what is tangent? Sine over cosine. Our sine here is negative pi. Our cosine is 0. We have -1. I said that wrong. Our sine is -1. We are looking here. Our sine is -1 because it's always the y sub u value. And our cosine is 0 because it's always our x sub u value. Well, anything divided by 0 is undefined. This is undefined, and I'm so glad we stumbled across this. That makes sense because generally in our parent function at negative pi over 2 for tangent, we will have, I don't know why I said generally, every single time for our parent function for tangent, we will have an asymptote at negative pi over 2. So we had that dilation that where we multiplied by that factor of 4. And so yeah, our x is our x is bigger. It's negative 2 pi that we plugged in there, but the vertical asymptote is still undefined. It's still undefined at that point. So we keep on going and we'll plug these in. The next one is -4 over pi. And again, I'm just going to do the counter angle. This is just a quick way of finding coterminal angles. You just kind of find it here. That's the positive version of it. And then reflect it across here. This is the negative version of it. So that's one of the quickest ways to do that. This is the negative version of negative pi over, or that is the negative version of pi over 4, or negative pi over 4. We're going to do the same thing. Tangent is sine over cosine. And I'm not writing that down because there's a lot of information here how these pieces go together. At this point, if we don't have that tangent is equal to sine over cosine memorized, I highly suggest you doing it. So we have this ordered pair that we were referencing. That's negative square roots of 2 over 2, negative square roots of 2 over 2, negative square roots of 2 over 2. And that is over, I love it. All right, that is over square roots of 2 over 2. Square roots of 2 over 2. There you go. Well, anything over itself is 1. We got that negative there. It doesn't really change much. So we'll have a -2 times -1, which is 2. And we'll keep on keeping on. We plug in 0. This one, plug in 0. 0 divided by 4 is 0. Tangent of 0. Now we're back to the easy angles. We're not looking at coterminal angles that are reflecting to find the coterminal angles. We're looking at the angles as they're given. Angle 0. That's angle 0 right there. It is a closed angle at 0. We get sine over cosine. 0 over 1. So we got 0 over 1 here. 0 over 1. Lucky for us, we can have 0 in the numerator. So this is 0 because 0 times -2 is 0. Moving on. These are hard problems, and these videos do get long because these are hard problems. We're connecting a lot of dots here. Or if we are taking pi, we plug it in, we find theta, we get pi over 4. We are looking at tangent pi over 4, and that is this angle right here. Tangent is sine over cosine, blue over red, square root of 2 over 2, over square root of 2 over 2. I couldn't have said that any faster. Square roots of 2 over 2 over square roots of 2 over 2. Whew, that's a lot. Lucky for us, that's one thing over itself. And anything over itself is 1. So we have -2 times 1, which is -2. And we are almost done. Plugging in x equals 2 pi to find theta. We will find theta is pi over 2. We take that pi over 2 and we plug it into tangent. We find tangent of pi over 2 on the unit circle. Well, that requires us to open our angle up to pi over 2. We will see that we end up getting 1 over 0 sine over cosine. 1 over 0 is undefined. So this is undefined. Was a mouthful. Now, before we graph this thing, it is important to know, what did we just find? Well, we found a vertical asymptote. We commonly just put VA there. We have another vertical asymptote. Anywhere your f of x is undefined for tangent functions, these will be vertical asymptotes. Then we already discovered our period. That was something that was asked on the student's worksheet. I'm just going to fill it out as is. I like to find this information before a graph because it helps me write a good graph. Notice I did not change that to f of x. That is not good graphing practices. So I'm going to leave that, change that to f of x so we know that's what we're graphing. It is important to note we have a developed table here. This table, we are only looking at the x and the f of x. Those are our ordered pairs that we would normally graph. We just use the unit circle to generate those, much like you would on a calculator. So our domain here, though, is a little tricky. Generally, teachers like to tell you start with what your domain can't be. So we found those asymptotes. So our asymptotes took place at the axes that were undefined. We were undefined, and I'm going to write this as asymptotes is the set of all x's such that x equals, that should be a set of all x's in the real number plane such that x cannot equal negative 2 pi. And we're going to have like a dot, dot, dot here, and you're going to see what I'm talking about here in a minute. Negative 2 pi, 2 pi, 4 pi, did that wrong, plus 4, which is 6 pi. You're going to see a pattern emerge. And generally, teachers want you to write that pattern rather than writing this out. Well, how can we more simply put that? Well, this is the set of all x's, and to be super specific, I do need to say x's in the real number plane such that x cannot equal, or these are asymptotes, so it is x, yeah, x cannot equal. You know what? This is a high school assignment. I'm probably going to confuse you if I put the students said that their teacher only needed this part, what x could not equal, and then to write the pattern a little more simply put. So I'm going to use my 2 pi here as our basis, and it's going to be plus 4 pi n such that n is an element of the integers. N is an element of the integers. We are an integer because if we take 1 and we plug it in for n here, we get 2 pi plus 4 pi, that's 6 pi. We plug in 2, we get 8 pi plus 2 pi, that's 10 pi. That's one of these. These do go on in either direction. And that's important. They do go on in either direction here, what x cannot be. So we could plug in -1. The only thing is that we can't have decimals or fractions for what we plug in for x. So we plug in -1, we get minus 4 pi. So 2 pi minus 4 pi. Well, that's not negative 2 pi. And we can keep doing that. So if we were going to write out our asymptotes super clearly, what x cannot be these things. Because these are our asymptotes. Now, with that being said, how do our asymptotes inform our domain? Well, if x can't be these things, then they're taken out of our domain. We want to write our domain very clearly. I want to say this is the set of all x's such that, set of all x's in the real numbers, such that x cannot be, and you just write, I wrote that wrong, x cannot be that formula. So we start at 2 pi. And honestly, we could just write 4 pi in there. No, we need that start at 2 pi. You can also start at -2 pi, but 2 pi plus 4 pi in. You can factor out 2 pi here if you want to, where n is in the real number, or where n is where N is not in the real numbers. N is in the integers, amount of the integers, because it has to be whole n value, but just not a decimal fraction. It can be positive. It can be positive. It can be negative. Now, here's what's cool. When we are looking at the range of our trig function for tangent, it doesn't change. It's the same no matter where we go. I'm going to go ahead and shrink down this domain so that way we can see the range a little more clearly without being in the way. If you are familiar with what these graphs look like, they're big ol' S's. They go forever and ever in the positive and negative direction as far as y goes. They go forever down, they go forever up. So forever is represented by negative infinity for forever down, and forever up is positive infinity. And that is the interval notation. So I did set notation for this one, interval notation for this one. You know, just showing you all the different notations today. We've answered everything here. We've not even sketched the graph. Look at all this information. Look at how long this video already is. And now we can sketch the graph. And we didn't have to memorize all these extra important pieces of information. We just had a few key pieces and we used that unit circle. So I do need to make sure this spans the proper amount. We'll call this negative 2 pi. I'm going to go pi here. 0, pi, 2 pi. Make sure you go full period at least on your graph. When you are dealing with vertical asymptotes, they are straight lines. They are vertical lines. They do go up and down forever in both directions. Do you need arrows on them? We generally show them as a dotted line. It's a little off. There we go. And so we're going to copy and paste that over here. Nope. I have no clue what I just did. Apparently nothing. Cool. And now we do this, and there you have your vertical asymptotes. Moving from there, we know this center, it wasn't shifted up or down, it's still at 0. Now, if you're good at memorizing these things, you know positive is like a positive x, but we have a negative here. Our a is negative. This is going to be a negative s. However, if you did not catch that, that's what this 2 and this was for. We know at negative pi, we are at positive 2. So this is supposed to be negative pi. I left off a sign there. Negative pi, we are at positive 2. We're going to call this 1. We're going to call this 2. We're going to call this negative 1. We're going to call this negative 2. So pi, we are at 2. Negative pi, excuse me. Negative pi, we're at 2. And at pi, we're at negative 2. Now we can see a little more clearly where our function goes. Now, tangent lines go forever, all right? So this is a little bit expand. Nope, that's not how that looks. Kind of like graphing on a whiteboard is hard. If you're one of my students, you know that. You see how frustrated I get with this thing every day. So while you watch me get frustrated with this thing, it's because where I'm going to grab this vertical asymptote and bring it out. I'm trying to scrunch it up and it's causing some issues. There's just not enough room for me to show the steepness like I'm wanting to. So I'm going to bring that up so I can look at the steepness a little more clearly with you. Looks something like this. Then we get like a little sway that happens here. And that same little sway happens like right here, but the opposite way. I don't know how to describe it. Like that, and it keeps going and going and going. The graph will never cross your vertical asymptote. All right, that's important. That is very, very poorly drawn on my end. Very, very, very poorly drawn. So, in the sake of awareness here, let me go ahead and grab that graph from Desmos. so you can see what it's supposed to look like because I am having a real hard time drawing that. So there we go. Here it is from Desmos. And you'll see it's pretty much that is what we got. Thank you so very much for your time and patience through this very long video of how to use the unit circle in order to find an X and Fx or X and Y table, T table, whatever you call it, your ordered pairs for your trig function to graph. And the number one thing is make sure you don't have repeating variables, that you don't have dual X's, you don't have dual Y's, and you should do just fine. All right. Thank you so much for your time. Your math knowledge has just been patched.